Testing one, two. All right. My name is Hunter, and this is week 8 for general chemistry content review. We are doing more redox reactions in electrochemistry. This is a really good review week because we're pulling in concepts from back at equilibrium. We're looking again at uh, half cell reactions, review of basic redox reactions. Um, So we're gonna kind of move through these pretty quickly, and I'll try to draw attention to the most important things to remember. I have in the top right here a summary of the equations that you might need um, for these problems, and you'll be referring to the textbook for a lot of tabulated values. So I've pulled those in um, for most of these problems, so you don't have to go hunting for them. But know that you will need tabulated values to solve a lot of these. All right, so electrode and cell potentials. Calculate the standard cell potential for each reaction below and note whether the reaction is spontaneous under standard state conditions. So when we're talking about standard cell potential, that is that E naught. Oh my gosh, why am I on my E naught with the little zero up top of the cell? Standard temp and pressure. So anyways, for this, we can find the standard cell potential by subtracting the anode half reaction from the cathode half reaction. So anox, um, the anode is the site of oxidation, and a red cathode is the site of reduction. So looking at these, we just have to decide which one is the site of reduction, and which species is accounting for the site of oxidation, which one's the cathode, which one's the anode, and write our equation that way. So I've already written our balanced equation here to just bring it down. Um, Looking at this, it would appear, oh, and I'm actually going to pull this over. We have our tabulated values here as well. So oil rig, oxidation is loss of electrons, reduction is gain of electrons. So which species is gaining electrons? Nickel goes from a positive 2 charge to a neutral solid. So that is our gain of electrons. Reduction is gain. That has to be our reduction. And red cat. So that is going to be reduced. That's going to be our anode. So our E naught cell equals that tabulated value for nickel. And I totally pulled over the wrong tabulated value. Okay, ignore that. Ignore that. That's for the next problem. The appropriate value here is negative 0.257. This is always in volts. We subtract the anode half cell potential, and that is negative 1.185. So subtracting a negative, we get addition. Crunch those numbers, 0.928 volts. Because we're dealing, come on, because we're dealing with standard cell potentials, we don't have to worry about stoichiometry for these problems, at least not yet. Once we get to combining balanced equations, then we're going to have to look at it again. But for these first couple of problems, stoichiometry, the stoichiometric coefficients are not an issue. I have also written some prompts up here talking about spontaneity. If your standard cell potential, if the E naught cell is greater than 0, then the reaction is spontaneous. We have a positive value for this first one. So that is a spontaneous reaction. Let's move on to B. Here we're looking at 3 copper, 2 plus in aqueous solution, plus 2 aluminum solid, transitions to 2 aluminum 3 plus aqueous plus 3 copper solid. Reduction is gain of electrons. Which one's gaining electrons? Copper is going from a 2 plus oxidation state to a neutral oxidation state. So that one is our cathode, redox reduction at the cathode. So our E naught cell, and again, we're not worried about the stoichiometry here, so we can just ignore all these numbers. We don't need them. E naught cell equals the standard half cell potential for the cathode, which is plus 0.34 minus the anode. For aluminum, that is negative 1.662. Subtracting a negative, we get a positive. And that is 0.928. Excuse me. I'm looking at the one up above. That is 2.00 volts. Again, this is a positive value. So this is spontaneous. All right. C gets a little bit more tricky. So I'm going to rewrite it down here. We have solid sodium plus lithium nitrate aqueous. And I actually don't need those parentheses because there's no, it's just one nitrate. But I'm going to leave the parentheses there so that we can kind of see how these ionic species are interacting with each other. So this is a simple exchange reaction. And we know that is a redox reaction. So all we really need to remember here is that in aqueous solution, the lithium is going to dissociate from the nitrate. We know nitrate always has a -1 charge associated with it. And so we can infer that the lithium has a +1 charge in this aqueous state. So I'm going to go ahead and pull this down. Same thing's going to happen here. Sodium has that positive state to balance out the negative on the nitrate. These are all aqueous species plus solid lithium. Our lithium is gaining electrons. That's the site of reduction. That is our cathode. And so we know what formula we need now. I'm going to go ahead and just tell you the value for that half reaction. See, I've written it over here. It's negative 3.04 minus for sodium is negative 2.71 minus a negative equals negative 0.33. So we have our first negative value. This is non-spontaneous. And I want to reemphasize, you have to be very careful with your signs. As long as you are doing E naught cathode, the standard cell potential of the cathode minus the anode, you don't have to change the signs from these tabulated values where the electrons are on the left of their respective half reaction equations. So if you're given these forward or backward, I guess, just keep track of what those positive or negative values might be. But if you do it this way, and again, E naught cell equals E naught cathode minus E naught anode, your signs will be really, really easy. All right, last one. We had calcium, actually, you know what? We're going to skip this one because it's exactly the same as we just did. You just have multiple nitrates, so that'll be +2 charge here, -2 total charge there. It's the same problem we just solved, just a little bit different. So if you want the answer key, calcium is your cathode, 2.868 minus a negative 2.912. That's your barium species, equals 0.044 volts. It's positive, so that is spontaneous. Very much the same problem. All right, question 24. Determine the cell reaction and standard cell potential at 25 degrees Celsius for a cell made from a cathode half cell consisting of silver electrode in 1 molar silver nitrate solution and an anode half cell consisting of a zinc electrode in 1 molar zinc nitrate. Is the reaction spontaneous at standard conditions? So they've done us a favor and already told us what our cathode and anodes are, but we need to go a little bit further now. And I'm going to pull in our tabulated values from over here. Easy peasy. E naught cell equals plus 0.7996 minus a negative 0.7618 equals 1.5614 volts. Spontaneous. It's positive, so it's spontaneous. It has been a long week, y'all. Looking forward to the long weekend. Okay, so that's half the problem. We have figured out the standard cell potential at 25 degrees Celsius, standard temp and pressure, right? We didn't have to change anything special about this. Now we need, come on now. Now we need the full cell reaction. And this is where our stoichiometry starts to matter, okay? So we have our half reactions, and I'm actually just going to go ahead and use these up here as a reference. So we have our cathode species keeps the electron on the left, and then we're going to have to flip the anode species, which is our zinc. And we're going to flip that around so that the 2 electrons associated with it are on the right side of this equation. So, and we need for those electrons to cancel out. So we're just going to multiply the silver side of this times 2. So we have 2 silver plus, this is aqueous, plus 2 electrons. The electrons are going to cancel out. So I'm going to go ahead and get rid of that. So we have our zinc species, solid, because remember, we're flipping that one around. Just to make that a little bit clearer. And then on our product side, we have solid silver plus our 2 electrons canceled out, and we have zinc aqueous 2 plus. 2 silver there. So standard cell potential, standard reaction, standard the cell reaction. Okay, I think that's everything. Okay, write a balanced cell reaction for the cell schematic below. Same thing that we just did, and calculate the standard cell potential. And note whether the reaction is spontaneous. So you can see I've already made some notes here for us, but this cell notation is simply anode on the left, 2 lines between them, cathode on the right. So we also need to pull in our tabulated values. It's cathode minus anode. Our cathode is that bromine species, The standard half cell potential for that is positive 1.0873 minus our anode. In this case, it's hydrogen. The platinum remains a solid on both sides, and that is a good indication that it is a spectator in these cells. We don't need it. As you get into organic chemistry, you will learn why platinum is used as a catalyst for reactions like this. And well, I don't want to get too in the weeds, but platinum facilitates the reaction. It helps catalyze it. It's not participating directly in the reduction or oxidation of species here. So we can ignore it. It's inert. So we have our cathode minus our anode. The standard half cell potential for the oxidation of hydrogen is 0. And so the standard cell potential, woof, is just 1.0873 volts. It's positive, it's spontaneous. We're not done. We have gaseous hydrogen separates, got our electrons on the right. So that's our oxidation of hydrogen. And then we have bromine, aqueous, plus 2 electrons, forms 2 bromines with their negative charge associated with it. We add these reactions together, electrons cancel out. We have aqueous bromine, electrons cancel out. We have dihydrogen gas. And on our product side, we have 2 aqueous hydrogen plus 2 aqueous bromide. And that is our cell reaction. Okay. We're cruising. We have a couple new variables for this one. We're going back to entropy and enthalpy a little bit. We've got standard free energy. Gibbs free energy is back. So for each pair of standard free energy change and electron stoichiometry values below, calculate a corresponding standard cell potential. So I'm just going to write this up at the top here. This is harking back to the gas law, which was PV equals nRT. The electron stoichiometry is another way of saying the number of moles of electrons participating in the redox reaction, and that is the value n in our ideal gas law. And we're looking at a slightly different form of this equation today, which includes Gibbs free energy and Faraday's constant. That equation, E naught cell equals negative standard Gibbs free energy of the reaction over the number of electrons times Faraday's constant, which is 96,485 coulombs per mole. You don't need to worry about that, units on that, but just good to know. If you are, for example, taking a standardized test where you might need to produce this number from memory, 96,500 is a common way of making the math a little bit easier for yourself. And if you really want to, 96,000 is a reasonable approximation of F, Faraday's constant. So let me make this a little bit smaller so that we can ideally do both of these. So we have a 12 kilojoules per mole is our standard free energy change. and an N of 3 for this first one. So we can just plug these numbers in. So negative 12 times 10 to the third, because we're in joules. Faraday's constant requires joules, over 3 is the number of moles of electrons, times Faraday's constant, 96,485. Plug that into your calculator. Should give you negative 0.041 volts. Moving on to the next one, we have negative 45 kilojoules per mole and N of 1. So same deal. E naught cell equals negative change in Gibbs free energy over moles of electrons over Faraday's constant, negative times a negative 45 times 10 to the third joules per mole, 1 times 96,485 gives us negative times a negative gives us a positive 0.47 volts. Just as a review, spontaneity when looking at Gibbs free energy, I believe is the other way around. Negative Gibbs free energy indicates a spontaneous process. So the way of thinking about that, Gibbs free energy, when it's negative, the system is losing that energy. It's putting energy into the environment. It's exergonic. It's energetically favorable. It is spontaneous. If it is a positive Gibbs free energy, it requires energy in order to proceed. So it is a non-spontaneous reaction. Okay. Question 29. Determine the standard cell potential and the cell potential under the stated conditions for the electrochemical reactions described here, and state whether each is spontaneous or non-spontaneous under each set of conditions at 298.15 Kelvin. 298.15 Kelvin is your standard temp generally. And we're given this mercury and sulfur and silver. And looking at this, it seems we have some liquid, aqueous, aqueous, solid, solid. Okay, so we can simplify a couple of things here. Silver is being reduced, it's gaining electrons, and it looks like, I think sulfur is our oxidized species. Yeah, loss of electrons. We're binding with mercury. Mercury is our spectator, we don't need it. Okay. Under standard conditions, E naught cell equals cathode, red cat, site of reduction. The tabulated value for silver, we've already seen this a couple of times, 0.7996, minus the anode, which we decided was sulfur. And that value from the text is negative 0.70. These are both in volts. So plus a positive, you get 1.4996 volts. That's your standard. That's your standard cell potential. Now, for non-standard conditions, we just remove that naught to show this. So E cell equals E naught cell, the standard cell, minus RTNF times the quantity ln Q. So we have a Q constant. This is an equilibrium constant. This is going back to solubility and equilibrium and everything else we did. Q is simply products over reactants. Yes, products over reactants. We are thankfully given some concentrations in this problem that we can pull in. So I already went ahead and wrote down some variables here. So we have, again, E naught cell and the reaction for the cell at non-standard conditions. We have our R value for energy, which is 8.314 joules over mole dot Kelvin. We have Faraday's constant. We have temperature, which they gave us was 298.15 Kelvin. And we have N equals the moles of electrons. And the way that they worded this is helpful up above when they were talking about electron stoichiometry, which I circled in red up top. This one's really easy because we only have one stoichiometric coefficient. We know that there's going to be 2 electrons involved in this. So our N equals 2. And then for Q, it's concentration of products. Remember, your coefficients refer to your stoichiometric coefficients, your exponent. Products raised to their coefficients over reactants raised to their coefficients. Our products are all solids. I'm going to highlight that in red real quick. Our products are all solids, so their concentration is 1. For liquids and solids, it's always 1. Don't have to worry about that. For our reactants, we had sulfur with no stoichiometric coefficient and silver raised to its stoichiometric coefficient of 2. So we have, from the problem, our concentrations were, I have to go back up to A here, 0.1 molar and 0.25 molar. Yep, got that. Raised the 0.25 to the second power, and that value is 160. So our Q value is 160. Let's pull these values over. So E cell, let's stick with blue. E cell equals, our E naught cell was what we calculated, minus R is 8.314. Temperature they gave us in Kelvin was 298.15. Our electron stoichiometry was 2. Faraday's constant is 96,000. I wrote 500. It's 485. We've been precise with everything else. We'll stick with the higher level of precision here. Times the quantity ln of 160. Okay, let's break that down a tiny bit. E cell equals, that's 1.5 if we stick to significant figures, minus 0.06519 is what I got, equals 1.43 volts. And that is our non-standard cell potential. This is also spontaneous at non-standard conditions. We're not done. Rather than going on to B, I'm going to pull the next question up, which is simply to determine the Gibbs-free energy and standard Gibbs-free energy for each of the reactions in the previous problem. So our Gibbs-free energy at non-standard conditions equals negative electron stoichiometry times Faraday's constant times the cell potential. So let's just pull these in. Negative 2, 96,485 times the number we just calculated, 1.43 volts, equals Let me check my work here. 2 times 96,485 times 1.43 equals negative 2.76 times 10 to the fifth. Now the standard gives free energy. Same formula. We just pull in the standard cell potential instead. So negative 2 times Faraday's constant times, from up above, 1.5 rounding up, significant figures, equals, sorry, negative 2.89 times 10 to the fifth. Okay. These two problems, A and B, are probably the best review problems that you can do if you do nothing else for this week's questions, just because it pulls in so many different concepts. I would say the next one, 31, is also included because we have another equilibrium that we need to figure out. All right. Use the data in Appendix L to calculate equilibrium constants for the following reactions. Assume 298.15 Kelvin if no temperature is given. There's no temperature given for A. That's the one I'm going to do. And it's, again, cathode minus anode. Looking at our equation here, it looks like oh, I already pulled this in. So these are our standard half reactions from Appendix L that you need to use for this problem. So our cathode is this second equation, and that's 0.22233 volts minus a positive 0.7996 volts. Use Appendix L to calculate equilibrium constants for the following reactions. Yeah, we still need to figure out what the standard cell potential is in order to calculate this value K. Is why we're going through this exercise, in case that wasn't clear. This isn't for no reason. And that is negative 0.5773 volts is our standard cell potential. So now we have a value that we can plug into this equation. So let's go ahead and pull that in. We have negative 0.5773 equals, value for R was 8.314. T was given to us as 298.15 Kelvin. All over electron stoichiometry was 1, so we can ignore it. Times Faraday's constant is 96,485 equals, excuse me, times the quantity lnk or lnq. K and Q are synonymous in this particular situation. It's just a variable. Okay, let's simplify what we can. Negative 0.5773 equals, this fraction comes out to 0.025691238. I'm leaving all of these long numbers in there right now for the sake of precision. We'll do our simplifying or our sig figs later, times ln(q). We divide both sides by this big long number, and we should get negative 22.47069 equals lnk. To get rid of the natural log, we raise e to that number. So on your calculator, just hit on your TI-98, at TI-84, you hit second ln and then the number you want to get rid of. So e raised to negative 22.47069 gives you your k value, which is 1.742 times 10 to the negative 10. And that is your equilibrium constant for this non-spontaneous reaction. It's non-spontaneous because we had a negative value there. Okay, I'm going to stop there for today. Um, enjoy the long weekend, y'all. Try and get outside, even if it's a little rainy. Um, rest, enjoy, and I will see you all next week.